In light of last week's election, it's clear two issues dominate the Australian political landscape: climate action and housing affordability. Our project, The Impact of Climate Change on Australian Residential Property Prices, marries the two. In 2021, the real estate market sold $350 billion worth of property, corresponding to 13% of GDP. The industry provides 25% of Australian jobs and is overwhelmingly composed of small businesses. 67% of Australians are homeowners. By 2060, climate change will amount to expenses worth $73 billion each year in Australia, regardless of action taken now and in the future. The Climate Council is estimating that 1 in 25 properties will not be insurable by 2030. Australia's narrow export base of iron ore, coal, and aluminium threatens our global relevance as the world moves towards renewables. Our project endeavours to quantify the consequences of climate change on house prices across Australia's capital cities. We chose temperature, rainfall, and solar exposure as our independent variables as the CSIRO and the UNEP, an international environmental panel, determines each of these as Australian weather factors highly influenced by climate change. We then constructed two models to explore this. First, investigating two panel models to determine these variables' mean and quantile effect on house prices, and second, an E-GARCH model for measuring the volatility on said house prices. We also incorporated macroeconomic variables including GDP, unemployment, and lending rates as controls. We were first drawn to the paper, Does Climate Change Affect Real Estate Prices? Only if you believe in it, which argued that climate variables only had a statistically significant effect on prices if they updated agents' beliefs on the value of a property. The conclusion that price changes are determined by agents' beliefs and preferences permeates the economic literature on real estate and underlies the causal chain of our study. It is the connection between climate variables and house prices. In another paper, researchers used hedonic regression to simulate and estimate the impact of global warming on real estate prices near ski resorts. This paper was insightful in its simple connection between three datasets: house prices and characteristics, weather conditions, and ski area characteristics. We therefore decided that our independent variables had to be reflective of climate change in each of Australia's capital cities. Finally, in reading house price volatility and its determinants, we were persuaded to employ a E-GARCH model, given their study found that the second moment's effects on house prices was more statistically significant than that of the first moment. And we opted for an E-GARCH model specifically, given both the intuition and empirical evidence that negative property price changes affect the market's volatility more than positive ones, which the exponential and asymmetrical E-GARCH model accommodates. I'll now pass on to Stella to talk about our data.
So here comes our data justification and description. Our panel data contains 8 capital cities with 7 cross-sectional variables over 77 quarters. We obtained our macroeconomic data from the ABS at a quarterly rate. We sourced our climate variables, temperature, rainfall, and solar exposure from Bureau of Meteorology at monthly intervals. Weather stations were chosen by their proximity to the city's central business district, and 1 station was selected per city. When there were missing values, we filled in blank cells by taking the average of observations of adjacent weather stations. The E-GARCH package required at least 100 observations. We confronted this by interpolation, which is to take the average of the previous and next period to create a new data point. The time-dimensional sample size was expanded from 77 to 105. When non-stationary data was used, the data may present a spurious relationship if it has unit rules. Also, any t-statistics generated would also be invalid, as they don't follow a normal distribution. Both of these will lead to incorrect inferences. So the ADF test is used to clarify if the data requires differencing to become stationary, and our results from ADF test are shown as follows. I will now pass on to Joysie to talk about our econometric models.
Our panel models and E-GARCH with exogenous variables are employed to parameterize the impacts of our climate change and macroeconomic variables on the value and volatility of the Australian housing market. Panel models measure the conditional mean effect of regressors, have the ability to eliminate time-invariant heterogeneity through time to meaning. Critically, this removes omitted variable bias, that is time invariant, AI, the need to include any time constant hedonic pricing variables, such as bedrooms and land size. Furthermore, we have conducted tests for structural breaks and stationarity of data using the Chow and ADF tests respectively. Any issues have been remedied and HAC robust standard errors estimated as conventional. So, fixed effects or random effects. Both adopt the classical linear regression model assumptions of linearity, full column rank, zero conditional mean of idiosyncratic error, and homoscedasticity. However, random effects imposes a stronger exogeneity condition on the entire composite error to include AI. The choice between fixed effects and random effects is contingent on the relationship between AI and the regressors. Hence, correlated random effects was run on Starter, which models AI as a function of xi bar. Alternatively, a Hausman test for equality of estimated coefficients between both regressions can be conducted. Our findings demonstrate that the gamma coefficients are jointly statistically significant, suggesting the use of fixed effects would be more appropriate. However, we acknowledge the drawbacks of a conditional mean approach. Climate change may have heterogeneous effects on the house price distribution. Panel quantile measures a regressor's conditional quantile effect and augments the understanding of how representative the fixed effects model is. Our team has decided to use Cuenca's 2004 model of quantile panel regression as given on the slide. The residual minimization process uses the check function rho, an indicator variable, to appropriately weight and transform residuals into least absolute deviation. The penalty coefficient lambda allows efficient estimation of AI. The quantiles chosen were 0.25, 0.5, and 0.75, and the panel estimated through a penalized fixed effect structure with bootstrap standard errors. I'll now pass on to Vicky to explain our volatility modeling.
Let me take you through our E-GARCH model. Firstly, the GARCH model was developed by Bolesev in 1986, allowing for the conditional variance to depend on past lags of error and its own variance. This adds an autoregressive part to the model. Unlike GARCH, E-GARCH applies a logarithmic form on the conditional variance, making our variance strictly positive. It is also able to measure asymmetry, giving us the ability to assess whether positive or negative shocks affect house prices more. We have added in our exogenous variables in matrix form into the conditional variance to assess each variable's effect on the volatility of house prices. This is measured by beta. Gamma will measure the asymmetry effect. If it is statistically significant and positive, then positive shocks increase volatility more. The E-GARCH model assumes the error terms to be normally distributed, but past literature has found volatility clustering in house prices. This relaxes the assumption of homoscedasticity. There is little consensus on which E-GARCH model should be used for financial data, but the GARCH 1.1 is the general specification for financial series, so we applied an E-GARCH 1.1 model. Having already tested for stationarity and different style data, we will now test for arch effects following these steps. We first fitted ARIMA models for the property price indices of each city using the order ARIMA function. Next, we tested for arch effects by taking the squared residuals of our fitted models to conduct the Lejeune box test. We found that Brisbane, Canberra, Hobart, and Adelaide exhibited volatility clustering. Although surprisingly, Sydney and Melbourne did not. This result is supported by an Australian study which found that the price movements in Australia's largest cities have been mostly homoscedastic, exhibit an upward trend, and are non-convergent with the pricing behaviour of other cities. Next, Esther will talk about our data analysis and results.
Our data analysis begins with our fixed effects model. As the data is a housing index, any partial effects represent a percentage point increase/decrease relative to the base year 2009. We found that temperature and lending rate are highly statistically significant regressors. On average, a 1 degree increase in temperature is expected to decrease the average Australian house price index by 0.37% ceteris paribus. This is consistent with the view that one of the main indicators of climate change has an adverse impact on house prices. However, rain and solar exposure are economically and statistically insignificant. Similarly, the macroeconomic variables behave as expected. A 1% increase in lending rate is expected to decrease the average house price index by 0.5%. GDP and unemployment have smaller partial effects, but a joint hypothesis reveals they are significant. This is likely due to a strong linear relationship that causes multicollinearity and inflated standard error estimates. I'll now pass on to Joanne to discuss our quantile results.
Quantile estimates reveal that there are indeed asymmetric effects of the regressors on housing prices. Notably, there is heterogeneity of quantile effect in temperature, lending rate, and GDP, mostly concentrated in the upper 75th percentile. This indicates that fixed effects mean estimates may not accurately represent the entire distribution of housing prices. As it has the highest degree of correlation to climate change, the majority of the climate change risk effects are concentrated in the temperature regressor. For example, a 1-degree increase in temperature will reduce housing prices by 0.78% in the 0.75 quantile compared to 0.33% around the mean. Even controlling for largely time-invariant factors such as average coastal distance and quality of neighborhood, this is likely due to more expensive properties being concentrated in areas or states with most climate risk exposure, such as Queensland or New South Wales. Furthermore, as Baldoff and Galapi suggested in 2020, housing prices are often influenced by attitudes and climate change belief, which is a variable that we unfortunately cannot control for. Often, expensive properties are located in relatively socially progressive states, such as New South Wales and Victoria. Consumer sentiment about climate change risk is then priced into property value, which results in a larger negative impact of temperature. Similarly, there is a disproportionate effect of lending rate and GDP on the 0.75 quantile. This effect is likely due to speculative properties and bubbles being concentrated in more expensive real estates, as suggested by Birkeland and Soderberg in 2020, which is sensitive to changes in macroeconomic factors. Now, Vicky will explain our E-GARCH results.
We found that in Brisbane and Hobart, all the variables are statistically significant at the 1% level, meaning that they do influence the volatility of house prices. Quite notably is that our 1 degree Celsius in Brisbane and Hobart is expected to increase volatility by at least 40% on average. Canberra and Adelaide, on the other hand, are mainly influenced by the macro variables. All 3 variables are statistically significant at the 5% level for both cities. In summary, rainfall increased volatility by 1.5% for Brisbane and Hobart, whereas rain was statistically insignificant for Canberra and Adelaide. As Brisbane and Hobart are prone to flooding based on their infrastructure and landscape, the increase in volatility is within our expectations. We found an approximate 40% increase in price volatility for Hobart and Brisbane, whereas Adelaide saw a decrease of 11% for hotter temperatures. Lastly, sun exposure decreased volatility of prices by around 15% in Brisbane and Hobart, but increased price volatility by 16% in Adelaide. These competing effects imply that Brisbane and Hobart are more susceptible to changes in temperature, while Adelaide is more robust. On the other hand, Brisbane and Hobart see a decrease in volatility when there's more sunlight, unlike Adelaide, who experiences an increase. The asymmetry effect in our E-GARCH model tells us how volatile the market is to positive and negative shocks. Hobart and Adelaide and Brisbane all have statistically significant asymmetry effects. In particular, positive shocks on Hobart and Brisbane decrease the volatility by around 72%, and a positive shock on Adelaide will increase the volatility by 102%. Now, I'll let Esther talk about the limitations of our study.
Our team faced some limitations in our ability to collect relevant data to use in our models. To act as indicators for climate change, we used temperature, rainfall, and solar exposure as they were most comprehensive. However, these are not necessarily the best or only measures to model climate change. We could have used carbon emissions or sea levels. Given climate change is not well defined as a variable, it would have been beneficial to be able to test the strength of correlation quantitatively rather than qualitatively. Furthermore, a larger cross-sectional panel size with individual households or postcodes would have been more ideal for asymptotics. Similarly, variables such as unemployment could have been more geographically varied for precision rather than taking a state average. We also recognize that our models' accuracy are therefore constrained by our data inputs. Problems such as omitted variable bias arising from the inability to control factors such as sea level, coastal distance, or consumer sentiment would likely bias the estimated coefficients. Furthermore, different factors can be influential for one region, but not necessarily for others. As our study analysed their impact on national scope rather than regional targeted, this tends to moderate the effect. Future research could be more tailored to specific geographical areas accounting for climate or housing characteristics. For example, rainfall would impact Queensland, New South Wales, or Tasmania more. A wider scope of consideration to include commercial property or the rent market would also be beneficial. Finally, I'll pass on to Joysie to conclude our presentation.
So, our panel models reveal that there is a significant impact further increases in temperature will have on overall housing market value, especially concentrated in higher exposure, higher value properties. Whereas in our E-GARCH findings, we find that specific cities such as Brisbane and Hobart are more susceptible to rainfall and temperature, whereas Adelaide is more sensitive to solar exposure. In conclusion, what does this mean for the future of our housing market? The implications of what our models found suggest the need to address the imminent issues facing Australia. Increasing temperatures, which imply more natural disasters or weather anomalies, may exacerbate volatility or decrease overall housing market value, which would lead to economic uncertainty. Ultimately, we hope our team has provided some valuable insight into the pressing topic of climate change in the context of the Australian housing market. Thank you for listening.